Okay, so now we've come up with a definition for areas and volumes. And so the way that we define areas is this vector space lambda 2b, which is the span of symbols of this form, modulo the relations of bilinearity and the alternating property. And so remember, the way to think about this is that a symbol like this represents the parallelogram spanned by v1 and v2. And two such symbols are related by these equivalence relations if their areas are related in the same way. And so two parallelograms are considered equivalent if they have the same area and the same orientation. And remember, to have a well-defined addition, we are considering the span of such symbols, so we can have formal combinations of these symbols. And the way to think about those formal combinations is like a disjoint collection of multiple parallelograms, which may lie in different planes. And we sort of generalize that to k-dimensional volumes and call that space lambda kv, where we're considering sort of a collection of k vectors here instead of just two vectors. So there's two sorts of problems with this definition. The first is that this point of we're going to have to consider multiple parallelograms in different planes, which may be incompatible, and sort of there's not really good geometric significance of adding up planes in different adding up parallelograms in different planes. And the second problem is that we sought out to find something which gave an area and an orientation to a parallelogram. And while we've sort of done that by saying two parallelograms are the same if they have the same area and orientation, we haven't quite achieved our goal because we've never actually said what the area is going to be. And so as I kept saying in the previous videos, you're going to need to impose some sort of special area axiom or special volume axiom, which tells you that, okay, we're going to pick some vectors, e1 and e2, and declare that the unit square spanned by these two guys has an area of 1. And then every other parallelogram has an area multiple of that, and that's how you can define areas once you have the area of some special square or cube or whatnot. And so in this video, the special area axiom will finally get time to shine, and we're going to actually, in order to incorporate this, redefine the way in which we talk about areas, in that we won't be talking about the parallelograms themselves, but instead we'll talk about some function. And this function will take in as an input two vectors, or in higher dimension k vectors, and the output will be the area or the k-dimensional volume of the parallelogram or parallel pipette spanned by these vectors. And so this solves both of our problems. First off, because it gives an actual numerical value to the area, which is just the output of the function. And secondly, it's not so bad adding up two different such functions because you're just adding up two functions instead of adding up two geometric objects. And so when we get to it eventually, what this will say is something along the lines of an expression like the integral of dx dy plus dx dz is not so bad because all you're doing is you're integrating dx dy and integrating dx dz and adding these two expressions together after integrating them. So these will sort of end up being like functions which represent areas, and then what that's saying is you evaluate one function, you evaluate the other function, and then add them up together. So let's get down to it. What we want to say is that if we have two vectors v1 and v2, then we want to figure out what the area of this parallelogram is. And so what we're going to want to do is construct some function which says v1 wedge v2 has an area which is given by a of v1 and v2. And so this function takes in as an input two different vectors and spits out a real number which represents its area. And so for now, again, we'll be considering the simplest case where v is equal to r2 and sort of area elements in r2, and then we'll generalize to higher dimensions. So as I've kept saying before, we're going to need to find a special square, which we're going to, or a parallelogram, which we're going to declare to have an area of 1. And so let's take these two basis vectors, e1 and e2, and declare that the span square has an area of 1. And so the way that we'll define areas is we'll say, okay, v1 and v2 is equal to some constant a times e1 wedge e2. And so the area of these two parallelograms, of these two vectors, is going to be that coefficient right there. So let's determine what that coefficient is going to be in the general case. And so let's say that v1 is equal to ae1 plus be2. And so this will just be the column vector ab. And v2 is equal to ce1 plus de2. And so this will be the column vector cd. And So if we write this out, then this expression will then become a e1 plus b e2 wedge c e1 plus d e2. And now we are free to use our bilinearity and alternating axioms. And first what we can do is we can fix this first vector and expand the second vector using the bilinearity. And this will look like a e1 plus b e2 wedge c e1. And then you add on a e1 plus b e2 wedge d e2. Okay. And now what we can do is we can fix the second vector and expand in the first vector, again using bilinearity. And so you get four terms. So this will be a e1 wedge c e1 plus b e2 wedge c e1 plus a e1 wedge d e2 plus b e2 wedge d e2. Okay, and now what we can do is we can use the bilinearity again to sort of bring these coefficients to the outside. So what this will look like is AC E1 wedge E1, and this will be BC E2 wedge E1, and so on and so forth. And so now we have four different terms, but we can now use our alternating axiom to sort of simplify them a bit. And so in the last video, we showed that any expression of the form EI wedge EI is going to be equal to 0. And the reason is that if you swap these two vectors, then you're going to pick up a negative sign, but that doesn't really change the expression, and so you get that this is equal to its own negative, which implies it must be equal to 0. And again, the way to geometrically think about this is you're sort of looking at a parallelogram which is spanned by a vector in itself, and that doesn't really have any two-dimensional area, and so it's going to come out to 0. So that tells us is that this term goes to 0, and similarly this term has an E2 wedge E2, so it's also going to 0. And so what we end up with is two terms, BC E2 wedge E1 coming from here, plus AD E1 wedge E2. And so remember how for a special area we said that E1 wedge E2 has an area of 1. And so here we have an E1 wedge E2, but here we have an E2 wedge E1. So what we can do is we can invoke our alternating axiom and swap these two and pick up a negative sign up front. And so what that'll tell us is that this is minus C E1 wedge E2. And so putting everything together, we get that our final answer is AD minus BC of E1 wedge E2. Okay, so now we finally come at the answer that if we declare that E1 wedge E2 has an area of 1, then the area of V1 wedge V2 is going to be this expression AD minus BC, which is again just the coefficient multiplying this. So the reason I went through this computation again, since we've already done it before, is that I wanted to sort of highlight that these bilinearity and alternating axioms are nicer when you want to do algebraic manipulations. Because last time we used our shearing and scaling axioms, and then we had to like solve some equations and set some things equal to 0 and divide. But here we didn't have to do any of that, and so this computation works for all possible cases, and there's no issues anywhere. And arguably, the derivation is just algebraically nicer than it was over there. But anyways, so now we want to have a nice way to express A of V1 and V2, not in terms of the coefficients, but in terms of V1 and V2 themselves. And the reason that we're going to do this is because what I'm hinting at is where we can choose two other basis vectors, E1 prime and E2 prime, and we can see how the area of V1 and V2 changes if we declare now that this parallelogram has an area of 1. And in order to do that, we're going to have to change the coefficients that we're working with here. So we see that the area of this parallelogram sort of depends on the coefficients of V1 and V2 in terms of these basis vectors. And so we can define two functions, epsilon1 of V and epsilon2 of V. And so the way that these are defined is its input is one vector and its output is going to be a real number. And what it is if V is equal to V1 E1 plus V2 E2, then epsilon1 of V is equal to V1, and epsilon2 of V is equal to V2. And so all this is saying is since E1 and E2 form a basis, any vector V can be expanded in a unique way as something times E1 plus something times E2. And all this epsilon1 is doing is it's finding the coefficient of E1, and this epsilon2 is finding the coefficient of E2. So you can sort of think about these as analogous to projection operators, except there's nothing going on with inner products here, but still sort of essentially projecting onto the E1 direction and projecting onto the E2 direction, and then giving you the coefficients there. So we can rewrite our expression AD minus BC as the following. We can rewrite it as epsilon 1 V1, epsilon 2 V2, minus epsilon 2 V1, epsilon 1 V2. And the reason is, well, just compare what's going on here. Epsilon 1 of V1 is A, epsilon 2 of V2 is D, which is what shows up here. And then epsilon 2 of V1 is B, and epsilon 1 of V2 is C. And those are the two things that show up here, and there's a negative sign. And so we see that this expression is just the area function of V1 and V2 that we wanted. So in terms of epsilon 1 and epsilon 2, we can define the area to be this expression. And so the thing is, this area is sort of also implicitly dependent on the vectors E1 and E2. And so what I'll do instead is rewrite the area function as being the symbol epsilon 1 wedge epsilon 2. So this wedge product doesn't actually mean anything over here. This is just a formal symbol saying that the area is taken with respect to these functions epsilon 1 and epsilon 2, and epsilon 1 and epsilon 2 are explicitly dependent on the choice of basis E1 and E2, because if we chose a different basis, then the coefficients would be different. And so this is just saying epsilon 1 wedge epsilon 2 evaluated on two vectors is the area of the parallelogram spanned by those two vectors, given that the area spanned by the two vectors E1 and E2 is declared to be 1. And so this gives us a well-defined notion of the area of any parallelogram. Okay, so let's first do some sanity checks to check to make sure that this function gives us sort of what we expect. So the first thing we expect is that if this function is giving us the area of the thing spanned by these two vectors as a multiple of this basis, then we expect that epsilon 1 wedge epsilon 2 of E1 comma E2 should be equal to 1. And indeed, we verify that epsilon 1 of V1, well, this is just E1, so this is going to be equal to 1. And epsilon 2 of V2 is also equal to 1. And epsilon 2 of V1, well, there's no E2 in the first component, so this will be 0. And epsilon 1 of V2, well, there's no E1 in the second component, so this will also be 0. And so indeed, we do get that this expression is 1 minus 0, and it is 1. And let's also compute epsilon 1 wedge epsilon 2 of E2 comma E1. So we expect that this will have the same area, but it'll be off by an orientation, so we want to get -1 out as our answer. And to see that, well, if we put epsilon 1 V1, well, there's no E1 component in this first vector, and so we get 0 here. Epsilon 2 V2, again, there's no E2 in the second component, and so we get a 0 here. But here we have an E2 in the first component, and so we get a 1 here. And we have an E1 in the second component, and so we get a 1 here. And so this becomes 0 minus 1 times 1. And so this indeed does give us -1. So this is nice because this function not only encodes area, but also encodes the orientation that we've been dealing with earlier. And so what I've been alluding to this whole time is that in linear algebra, we don't have a preferred basis. So what that means is that we could have chosen an arbitrary basis, like say this guy, E1 prime and E2 prime, and we could have said, okay, what is V1 wedge V2 as some multiple A prime of E1 prime wedge E2 prime. And so what this is in effect saying is that if we declare this parallelogram, the parallelogram spanned by these two vectors to have area 1, then now what is the area of V1 wedge V2 prime? And so you can go through a similar game here and have sort of basically the same properties. And we'll define two new functions now, epsilon 1 prime and epsilon 2 prime. And the way that these work is if a vector v is equal to v1 prime e1 prime plus v2 prime e2 prime, then epsilon 1 prime of v is equal to v1 prime, and epsilon 2 prime of v is equal to v2 prime. And then we can similarly construct an expression, epsilon 1 prime wedge, epsilon 2 prime. And so as you expect, this will essentially be the same as this expression, except you v1 and v2, except now you just put in these primes everywhere. Okay, so let's work this out in an example and see what we get. So let's say that we have our initial basis, E1 and E2. So now let's put a new basis. Let's say E2 prime is equal to 2 times E2, and E1 prime is equal to 3 times E1. And so now we have from this expression, from this definition, that A prime should be equal to epsilon 1 prime wedge epsilon 2 prime evaluated on V1 and V2 times this area. So this quantity is equal to A prime. And so let's try to compute this A prime for E1 wedge E2. So in other words, we'll replace V1 and V2 with E1 and E2 and try to compute what this A prime is going to be. So in order to do that, we have epsilon 1 prime E1, epsilon 2 prime E2, minus epsilon 2 prime E1, epsilon 1 prime E2. And let's see what this is going to look like. Well, since E2 prime is 2E2, we have that E2 is equal to 1/2 E2 prime, and E1 is similarly equal to 1/3 E1 prime. And so that means that evaluating E1 prime on E1, epsilon 1 prime on E1 is going to give us the coefficient of E1 prime when we write E1 in terms of this new basis. And so this will be 1/3. And epsilon 2 prime, well, that's the coefficient of E2 prime when we express E2 in terms of this new basis by that definition. And so this should be 1/2. And then epsilon 2 prime of E1, well, there's no E2 prime here, so this is going to be 0. And this is also going to be 0. And so what we get is that A prime is equal to 1/6 E1 prime wedge E2 prime. And so this is kind of interesting because we've scaled our basis vector by 2 in one direction and by 3 in the other direction, and we've gotten a factor of 1/6, which is sort of 1 divided by the scaled area. So what's going on here is you're saying that this new bigger rectangle now has an area of 1, and so our smaller square has an area of 1/6 times the area of this new bigger rectangle. And so this allows us some flexibility in being able to say what the area of any shape is, because we can declare any parallelogram that we want, spanned by any basis that we want, as being an area of 1, and then express any other pair of vectors in terms of this basis and then computing the area that way. And the thing is that once we know this relation, since in 2 dimensions, basically all areas are considered equal, they can all be transformed into one another by sharing and scaling, we should be able to compute V1 wedge V2 in terms of this guy once we know what E1 wedge E2 is in terms of this guy. And so what I mean by that is V1 wedge V2 is equal to this, but this is just equal to E1 wedge, sorry, epsilon 1 wedge epsilon 2 of V1 comma V2. Times E1 wedge E2. But E1 wedge E2 is 1/6 E1 prime wedge E2 prime. But now this epsilon 1 prime wedge epsilon 2 prime was pretty much defined to be the coefficient here of this V1 wedge V2 in terms of this new basis E1 prime wedge E2 prime. And so what we find is that epsilon 1 prime wedge epsilon 2 prime of V1 V2 is equal to this whole quantity over here. So it's equal to 1/6 epsilon 1 wedge epsilon 2 of V1 V2. Okay, so this is nice. It says that this epsilon 1 wedge epsilon 2 is essentially saying, let's compute the area of these two, the parallelogram spanned by these two vectors with respect to this small square. And this is saying, let's change our basis and express the area in terms of this bigger rectangle. And the thing is that once we know the areas in terms of one of the basis, we automatically know the area of the other basis, as long as we can compute what sort of the fundamental parallelograms are with respect to one another. So here, the old square is 1/6 of the big square. So any area in the new system will be 1/6 of the area that it was in the old system. We can try this process in general and say, okay, let's choose some other arbitrary basis and then compute what the area of E1 and E2 is in this new basis. And then we get an appropriate scale factor to put in here to relate epsilon1 prime, epsilon2 prime in terms of epsilon1 wedge epsilon2. And so these are basically things that are functions which give us our area, right? So this is saying if we try to compute our area in two different ways, can we relate the two? And you can do that, but you're going to have to either go through bilinearity and the alternating property every time in order to compute the scale factor, or sharing and scaling. And sort of you might ask, is there a more direct algebraic way to do it? And at the end of the day, we will have to still use the alternating and bilinearity property, but it'll sort of be more direct in that we won't have to compute the multiple of these fundamental parallelograms. And so in order to do that, let's first try and understand what these epsilon i's actually are. Okay, so notice that from the definition of the epsilon i's, it's pretty clear that epsilon I of v plus v prime is equal to epsilon I of v plus epsilon I of v prime, right? Because all you're doing is you're adding up the coefficients, and you can either add up the coefficients and then look at the add up the vectors and then look at the coefficient, or you can look at the coefficients of each vectors and add them together. So that's just saying if you have a plus a prime and b plus b prime, then the coefficient of the first guy, you can either look at the coefficient here, or you can say, okay, this is the coefficient of a plus a prime. And similarly, we also have that epsilon I of alpha v is equal to alpha epsilon I of v. And this is also fairly clear. And so what that tells us is that these are really linear, not just any functions of our vector space, but these are linear functions of our vector space. And since the image is a real number, what this tells us is that each epsilon I is an element of the vector space of homomorphisms from V to R. And so this is saying that each epsilon I is a linear map from our vector space to the real numbers. And this is often written as V dual. So this is an important definition, so let's put it on the left. V dual is defined as hom from V to R. And then we notice that epsilon I and epsilon I prime as well are elements of V dual. Okay. So now the thing is that epsilon 1 and epsilon 2 are defined once we fix the vectors e1 and e2, and epsilon 1 prime and epsilon 2 prime are defined once we fix the vectors e1 prime and e2 prime. So the question is, if we change our basis from e1, e2 to e1 prime and e2 prime, can we relate the new dual basis, epsilon 1 prime and epsilon 2 prime of the dual vector space, to epsilon 1 and epsilon 2? And so the reason I call this a dual basis is because you can show that V star, V dual, is a two-dimensional vector space. And the way to do that is basically all elements of the homomorphism from V to R must be of the following form. If you have some vector V is equal to AB, then any epsilon in V dual is of the form CD. And then what you have is that epsilon of V is the multiplication of this row vector CD times this column vector AB, and then you get the quantity AC plus BD. And so here you have, basically that's saying that the dual vector space is represented by row vectors, and here since you have two numbers, it's a two-dimensional vector space, and these two guys are linearly independent, because, for example, epsilon 1 of E1 is equal to 1, while epsilon 2 of E1 is equal to 0. And so you can check that they aren't multiples of each other. And similarly, these two guys are linearly independent. And so we want to basically say that epsilon I prime is equal to some matrix B times epsilon I if the EI prime is equal to some matrix A times the EI. So what this is saying is you have some old basis vectors, E1, E2, and then you have new basis vectors, E1 prime, E2 prime, related via some change of coordinates A. And then you want to see, okay, can we change these dual functions, which sort of give projections onto E1 and E2, into the functions which give projections onto E1 prime and E2 prime. And it turns out that B is equal to A transpose inverse. And this is also equal to A inverse transpose because it doesn't matter in what order you do it. And this is quite an annoying formula, in my opinion. It's a bit annoying to understand, and the best way to really understand it is go through examples. But I will quickly give a proof of this first. And this is sort of why when we take the determinant of this transformation matrix in our earlier case, we would get 6. But when we look at the scaled volume, we got a factor of 1/6. And so this is related because the determinant of the inverse matrix would be 1/6. So let's see why this is true. So notice that if we take epsilon I of ej, then this is equal to 1 if I is equal to j and 0 otherwise. So in other words, epsilon 1 of E1 is 1 and epsilon 2 of E1 is 0, and same with the other cases. And so this is usually written as a function delta ij, and delta ij just means, okay, look at these two coefficients, and if they're the same number, then give it a 1, otherwise evaluate it to be 0. And the same thing holds for epsilon I prime of ej prime. Okay, so now I'll write these expressions out a bit more explicitly and say that ej prime is equal to the sum over k of a sub jk ek. And what we want to do is compute the coefficients b. So what that amounts to saying is that epsilon I prime is equal to the sum over L of b I L epsilon L. And so this is just writing matrix multiplication out in terms of numbers. And let's plug that into the expression that this is equal to delta ij. So we have epsilon I prime ej prime is equal to the sum of b I L epsilon L times evaluated on the sum of a jk ek. And well, now BIL and AJK are just numbers, and you can check that the linearity all works out. And this is equal to the sum over K and L of BIL AJK of epsilon L of EK. And so basically that happens because if you multiply this inside by some scalar factor like AJK, then you can move to the outside. And this is just taking the sum of different functions, and that's what we're doing in the right-hand side as well. Okay, now we can use this relation, which says that this is equal to 1 if and only if k is the same as L, and it's equal to 0 otherwise. So what that means is that we don't get any contributions here except when k equals L. And when we do have k equals L, then we get a contribution of 1 from this. So this is just the sum over k of b sub ik because k equals L, a j k. And remember that this should be equal to, from this first line, delta ij. Okay. So in matrix notation, delta ij corresponds to the identity matrix, because the identity matrix is the thing that has 1 along the diagonals, and zeros everywhere else. And this expression almost looks like matrix multiplication. So it would be matrix multiplication if the k and j were switched. Because over here, basically, our convention is that the second index is the thing that multiplies the vectors. And so what we almost have is that b times a is equal to the identity matrix, but instead we have to switch these around, and then we can do that so long as we take the transpose. Because if you switch the indices, that's the same thing as taking the transpose of your matrix. And what we end up with is the matrix equation that B A transpose is equal to the identity matrix. And so that implies that B is equal to A transpose inverse. Okay, so that's nice. Now we have a way of relating these new dual basis vectors in terms of our old ones, so long as we know this linear transformation. But let's sort of work that out in a bit more of an example. Okay, so let's say that our old basis looks like this, E1, E2, and let's say our new basis is E1 prime is equal to E1, and E2 prime is equal to E1 plus E2. So in other words, the first vector is going to look like that, and the second vector is going to look like this. And so now we want to compute epsilon 1 prime and epsilon 2 prime. Okay, so by what we've just derived, we have that the matrix A is equal to 1, 1, 0, 1. And the matrix B should be A transpose inverse or A inverse transpose. And so what that tells you is that the matrix B is equal to 1, minus 1, 0, 1. Because the inverse is pretty much putting a negative sign here, and then taking the transpose swaps the off diagonal. So what that tells us is that epsilon 1 prime is equal to epsilon 1 minus epsilon 2, and epsilon 2 prime is just equal to epsilon 2. And so this is a bit interesting because even though we have changed the second basis vector, what we've changed over here is actually the first dual basis vector. And so let's work out to see that this makes sense. Let's compute epsilon 2 prime of E2. Well, E2 is equal to, epsilon 2 prime of E2 prime, and we expect that this should be equal to 1. And this is equal to epsilon 2 prime of E1 plus E2, which, since we said epsilon 2 prime is equal to epsilon 2, this is just epsilon 2 of E1 plus E2, which is equal to 1, as we expect. And epsilon 2 prime of E1 prime is going to be equal to epsilon 2 of E1. And because there's no E2 over here, this is equal to 0. Okay. Similarly, let's look at epsilon 1 prime of E1 prime. And so this is equal to epsilon 1 minus epsilon 2 evaluated on E1. And so the way that we do this is we sort of distribute the E1, and this is equal to epsilon 1 of E1 minus epsilon 2 of E1. And this is equal to 1, well, this is equal to 0, so it's equal to 1, as we expect, because we want this to be equal to 1. And now is the interesting case where you look at epsilon 1 prime of E2 prime. So this is equal to epsilon 1 prime minus epsilon 2, epsilon 1 minus epsilon 2 of E1 plus E2. Because E2 prime is equal to this, and epsilon 1 prime by this formula should be equal to this. And so what happens is that if we apply epsilon 1 on this case, then we get 1. But so what that means is that epsilon 1 prime could not just be epsilon 1. Because if we evaluate on E2 prime, we expect to get 0. But if it was just epsilon 1, then we'd get a value of 1. But the minus epsilon 2 gives us a fact that if we evaluate epsilon 2 on this, we get another 1. And the negative sign gives us a negative 1, and so that gives us 0. And so that means that epsilon 1 prime of E2 prime does evaluate to give us 0, as we expect. And so this is something that I feel was not emphasized enough when I learned about this for the first time, which is that the dual basis depends on your initial basis as a whole. So epsilon 1 prime, even though we label it as a 1, it doesn't only depend on the first basis vector. It also depends on all of the other basis vectors that you have. And this is sort of related to when you take partial derivatives, sometimes you have to be careful about which variables you're holding fixed. And usually this is not written out explicitly. I think it is in thermodynamics, but otherwise not really. But it actually does play an important role because as we'll see later, derivatives are sort of analogous to this dual basis thing. And the dual basis really does depend on the entirety of your basis, not just the one particular vector that it's labeled by. Okay, so now we understand what these epsilon I symbols look like and the epsilon I prime. They're dual vectors and they form a basis of the dual vectors. And we found a way to say that if we change our basis into a new basis ei prime by matrix A, then this is how the dual basis should change. And so what this means is that the epsilon i's are pretty much projections onto the ei vectors, the coefficients of those, and the epsilon I primes are the coefficients of the projections onto the ei prime vectors, and we have a way to relate that as so. But our real goal was to relate things about areas. So we had the symbol, epsilon 1 wedge epsilon 2, which is a function of two vectors. And it is this following function. And epsilon 1 prime wedge epsilon 2 prime is the same function, except replace all the epsilons with epsilon primes. And so these pretty much give us two different ways of describing areas. The first one says that the area spanned by E1 and E2 is 1. And the second one says that the area spanned by E1 prime and E2 prime is 1. And so again, because the algebra has no preference for basis, these are both sort of equally justified ways to define areas of arbitrary parallelograms. And we saw that they differ by some scale factor, which is essentially how much the area of this thing is in terms of this new basis. So what fraction of this new area is this original area? And we have a way of knowing how these epsilon i's transform. And so the question is, can we figure out a way that these transform? And so now finally, I'll be explaining why I use this wedge symbol here, and also why it wasn't a complete waste of time to talk so much about the wedge product in this case, because it turns out that these dual vectors and this area element, or this two form, forms this wedge product relation in its own right. So in other words, these epsilon i's and epsilon I primes satisfy the alternating and bilinearity condition. And remember the way that we proved that in this case was by looking at shearing and scaling. And so we can do the same sort of process, and scaling isn't too difficult because if you have two vectors e1 and e2, and you sort of scale the second basis vector by some factor, let's say like 2, and call this e2 prime, then we know that epsilon 2 prime is equal to 1 over 2 epsilon 2. And we have that, so pretty much this gets scaled by a factor of a half. And we also have that this original square is half of the area of the new rectangle. So if the new rectangle has a new area declared to be 1, then this original square will have an area declared to be 1/2. And so what that tells us is that alpha epsilon 1 wedge epsilon 2 is equal to alpha times epsilon 1 wedge epsilon 2. And so now the scalar multiplication also makes a bit more sense because this is a function of two variables and this is a function of two variables. And it sort of makes sense to literally multiply a function by some scale factor. And so now we want to prove an analog of the shearing property. And the shearing property looks something like this. So you want an analog of something that looks like epsilon 1 plus alpha epsilon 2 wedge epsilon 2 is equal to epsilon 1 wedge epsilon 2. And so the good news is that this is actually fairly straightforward to prove. And the way to do that is, say we want to apply some transformation, which takes epsilon 1 to epsilon 1 plus alpha epsilon 2 and epsilon 2 to epsilon 2. So this tells us is this matrix, which I called B earlier, should be equal to 1 alpha and then 0, 1. And so what that tells us is that our transformation matrix A for the original vectors is going to look like 1, negative alpha, 0, 1. And so in other words, what we have is the first basis vectors get sent to itself. So E1 is equal to E1 prime. But the second basis vector gets altered, and in particular, it gets shifted to the left by alpha E1. So if this is E2, then E2 prime is equal to minus alpha E1 plus E2. Um, and now we want to compare the area of this unit square to the area of this sort of shifted parallelogram. But the good news is that we've already discussed this in the very beginning. Well, this is just a shearing procedure. And so that means that these two areas will be the same. And so what that tells us is that the wedge product of these two guys is going to be the same thing as the wedge product of these two guys, and that proves our claim right here. So the shearing property over here translates directly from the shearing property of areas, and we showed that in 2 dimensions, these two properties are equivalent to the bilinearity and the alternating property. And so what that tells us is that we can sort of use the same tricks from before and deduce that the scale factor must be the determinant of the transforming matrix for these dual basis vectors. And in essence, what that tells us is that this constant C is equal to the determinant of this guy, which is A transpose inverse. And this, the determinant of the inverse of a matrix is 1 divided by the determinant of a matrix. And the determinant of the transpose of a matrix is the same as the determinant of a matrix. And so what that tells us is that if we change our basis by some matrix A, then the area is changed by a factor of 1 over the determinant of A. And so this explains earlier how we sort of scaled our entries by a factor of 3 and a factor of 2, and that would give us a determinant of 6, but the area is scaled by a factor of 1/6. And this sort of makes sense because it says our old area is 1 divided by the determinant times the area of our new thing. And so finally, we come to our definition of k-forms, or in this case, 2 forms. So 2 forms are defined as lambda 2 of v star. And so what this is just formal linear combinations of these functions, which are epsilon I wedge epsilon, or epsilon 1 wedge epsilon 2, with epsilon I lying in, this time, the dual vector space. And the point of this is that, oh yeah, also modulo the 2 relations which are up here. And the point of this is that any omega in lambda 2 v star is the sum of these guys. And each of these is a function of 2 variables. So omega defines a function from v cross v to r, which sort of tells you a way to define an area of the parallelogram which is spanned by 2 vectors. So omega of v1 comma v2 is sort of related to gives you a way to define the area of v1 and v2. Okay, so this is finally the way that we're going to describe areas in a way that is suitable to work with calculus in Rham cohomology. And so now that we have discussed the case for 2 dimensions, let's generalize to higher dimensions and see what technicalities come out there.